Buckle up, it's space time. Number 10. The Pioneer Anomaly. In 1972, NASA launched Pioneer 10 into the void. It was a quarter-ton spacecraft designed to become the first human-made object to cross the asteroid belt, fly past Jupiter, and keep going forever. Engineers at NASA's Jet Propulsion Laboratory in Pasadena knew exactly where it should be at every moment. Then, in the early 1980s, they noticed something impossible. It was in the wrong place. Pioneer 10 and its sister ship, Pioneer 11, launched in April of 1973, were both drifting off course. Not by much, but by a measurable, persistent, and identical amount, an unexplained sunward acceleration of 8.74 times 10 to the negative 10 meters per second squared. Over a single year, that tiny force was enough to put the spacecraft nearly 400,000 kilometers behind where the laws of physics said it should be. The same anomaly on two separate spacecraft launched years apart. For 3 decades, no known force could explain it. Gravity had been accounted for. Solar radiation pressure had been modeled. Gas leaks, measurement error, gravitational effects from undiscovered planets. All had been considered and dismissed. Physicist John Anderson and his team at JPL documented the discrepancy meticulously across nearly 30 years of tracking data, and the anomaly refused to vanish. It appeared to be genuine, persistent, and deeply strange. The resolution came in June 2012 when physicist Slava Turyshev and colleagues published a paper in Physical Review Letters demonstrating that anisotropic thermal radiation from the spacecraft's own power supply was creating a tiny but real recoil force. Once properly modeled, the anomaly disappeared entirely. The universe had not broken any laws after all. But here's why we begin here. For 30 years, 2 spacecraft appeared to be defying physics, and our best models could not explain them. If something that mundane could fool the finest minds in planetary science for 3 decades, consider what we might be missing when we look at things far stranger and far less explainable. Number 9. Neutron stars. Matter that shouldn't hold together. On November 28, 1967, a 24-year-old PhD student named Jocelyn Bell sat down to review data from the Mullard Radio Astronomy Observatory in Cambridge and found a signal so regular, so impossibly precise, that her team briefly labeled its source LGM-1, Little Green Men. The signal was later understood to be a pulsar, a rapidly rotating neutron star, and what it revealed about the nature of matter remains one of the most disturbing facts in all of physics. A neutron star forms when a massive star collapses in a supernova, compressing its core so violently that protons and electrons are forced together into neutrons. The result is an object roughly 1.4 times the mass of our entire sun, crushed into a sphere no wider than 20 kilometers across. A teaspoon of its material would weigh approximately 10 million tons on Earth. Surface gravity runs to roughly 200 billion times what you feel standing on this planet. What makes neutron stars genuinely unsettling is not their density. Remarkable as that is, it is what happens at their cores. At the pressures found in a neutron star's interior, our equations of state simply stop working. The physics we use to describe matter at extreme densities produces contradictory answers. We cannot say with any confidence whether the core contains pure neutron matter, quark-gluon plasma, strange quark matter, or some exotic state of matter with no laboratory analog and no confirmed theory. We can observe them with extraordinary precision. The fastest known pulsar, PSRJ 1748-2446 AD, discovered in 2004, spins 716 times every second, a city-sized object rotating faster than a kitchen blender. We can measure their masses, their magnetic fields, their pulse timing down to microseconds. Yet 1 centimeter below the surface, our understanding hits a wall of genuine ignorance. We can track a neutron star across thousands of light years and describe its rotation to 11 decimal places. We cannot describe what it is made of. That gap between what we can observe and what we can understand is not a detail. It is a fundamental crack running through our model of physical reality. Number 8. The Alcubierre drive, the warp engine that physics allows. In 1994, a 30-year-old Mexican physicist named Miguel Alcubierre published a paper in the journal Classical and Quantum Gravity with a title that sounds like science fiction: The Warp Drive, Hyperfast Travel Within General Relativity. He was not writing fiction. He was solving Einstein's equations, and the solution he found described a spacecraft that could travel faster than light without technically moving at all. and the mathematics did not break. Einstein's special relativity forbids any object with mass from reaching the speed of light. The closer you get, the more energy you need, approaching infinity as you approach the cosmic speed limit. But Alcubierre found a loophole buried in general relativity, the theory that describes not just motion but the geometry of space-time itself. His proposal does not accelerate a ship through space. It compresses space-time ahead of the vessel and expands it behind, allowing the craft to sit inside a flat warp bubble while the universe moves around it. The ship never locally exceeds light speed. It just rides a wave of bent geometry. The design is technically valid. Independent physicists have examined Alcubierre's metric and found no internal contradiction with general relativity. The reason we cannot build one comes down to a single brutal requirement. The drive demands exotic matter with negative energy density, a substance that would repel rather than attract, and that exists in our universe only as a theoretical construct. No source of negative energy dense enough to fuel an Alcubierre drive has ever been identified. In 2021, physicist Eric Lentz at the University of Göttingen proposed a modified version of the drive that he argued could operate using only conventional positive energy, a development that generated serious discussion in the theoretical physics community. Harold White at NASA's EagleWorks laboratory has also conducted preliminary theoretical work on scaling the energy requirements down. Both efforts remain deeply speculative. The equations permit faster than light travel. General relativity, the most rigorously tested theory in the history of physics, does not prohibit it. The barrier is not the mathematics, it is the matter. And somewhere in that gap between what physics allows and what the universe provides, one of the most tantalizing questions in science sits quietly waiting. Number 7, quantum tunneling, the phenomenon that should not exist but powers the sun. Every second, inside the core of the sun, hydrogen nuclei are doing something that classical physics says is completely impossible. They are approaching each other, encountering an electromagnetic barrier they do not have sufficient energy to cross, and then appearing on the other side of it anyway. Without this phenomenon, nuclear fusion in stars could not occur. The sun would go dark. Life on Earth would never have arisen. And physics, as understood before the 20th century, has no mechanism to explain how any of it happens. The phenomenon is called quantum tunneling. In 1928, physicist George Gamow developed its mathematical framework to explain radioactive alpha decay, the process by which a particle escapes an atomic nucleus. It seemingly lacks the energy to leave. The following year, Gamow, Robert Atkinson, and Fritz Houtermans applied the same principle to stellar fusion, explaining for the first time how stars generate energy. Classical physics gives a particle near zero probability of crossing an energy barrier it cannot surmount. Quantum mechanics gives it a small but non-zero probability. And in a star, where the numbers involved are almost incomprehensibly large, small but non-zero is more than enough. What elevates tunneling from a theoretical curiosity to something genuinely unsettling is that we exploit it in everyday technology. The tunnel diode, invented by Leo Esaki in 1957, for which he was awarded the Nobel Prize in 1973, is a semiconductor device that functions entirely because electrons pass through barriers they classically cannot cross. The scanning tunneling microscope, developed by Geert Binnig and Heinrich Rohrer, who shared the 1986 Nobel Prize, images individual atoms by measuring quantum tunneling current flowing across a gap. These are not theoretical demonstrations. They are commercial devices manufactured in the billions. More disturbing still, recent research suggests quantum tunneling may play a role in DNA mutation and enzyme catalysis, meaning that the same rule-breaking phenomenon that powers the sun may be woven into the molecular machinery of life itself. A particle is on one side of a barrier it cannot cross. Then it is on the other side. There is no classical trajectory between those two states. Quantum tunneling is not an approximation or a model. It is directly measured, commercially exploited, embedded in the chip running the device you are watching this on. So the question is not whether particles break the classical rules. The question is why the universe was built with that particular loophole written into its foundations. Number 6, white holes, the objects that physics demands and reality may refuse. General relativity is the most precisely tested theory in the history of science. It predicted the bending of light by gravity before we could measure it, described the orbital decay of binary pulsars decades before we could verify it, and forecast gravitational waves a century before the LIGO detector heard space-time itself ripple in September 2015. So when general relativity predicts something that seems impossible, the burden of proof is extremely high. And it predicts white holes. A black hole is a region of space-time from which nothing can escape. Its event horizon is a one-way membrane. Matter and light can fall in, but nothing ever comes out. The Schwarzschild solution to Einstein's field equations, which describes a black hole's geometry, has a time reverse that is equally valid mathematically. That time reverse is a white hole, an object whose event horizon is a one-way membrane in the opposite direction. Nothing can enter. Everything must escape. The same equations that give us one give us the other, as inevitably as negative numbers emerge from algebra. The problem is thermodynamics, specifically the second law. Entropy in a closed system always increases or stays the same. A white hole, which perpetually ejects matter and energy while emitting nothing, would cause entropy to decrease in its vicinity, a direct violation of one of the most fundamental constraints in all of physics. So we have a genuine confrontation. Two of our most trusted theories, general relativity and thermodynamics, pointing in opposite directions. In 2014, physicist Carlo Rovelli and colleagues proposed a resolution. They argued that white holes might be the natural end state of black hole evaporation, the final stage after a black hole has radiated away its mass over astronomical timescales via Hawking radiation. Under this model, the contradiction with thermodynamics is resolved through quantum gravitational effects. Some researchers have gone further, suggesting that the Big Bang itself may have been a white hole event. Both proposals remain theoretical. Black holes are confirmed. We have imaged them. We have detected the gravitational waves from their collisions. The same equations that confirm black holes also demand white holes exist in the mathematical structure of space-time. We simply have not yet decided whether the universe has chosen to honor that demand. Number 5. The Casimir effect. Energy appearing from nothing. In 1948, Dutch physicist Hendrik Casimir was working through the mathematics of quantum field theory when he arrived at a prediction so counterintuitive he reportedly found it difficult to believe himself. He calculated that two uncharged, perfectly flat metal plates, placed close enough together in a complete vacuum, would be pushed toward each other by a force with no classical explanation. No charges, no fields, no contact. Just two plates, a vacuum, and a measurable force generated by nothing. In January 1997, physicist Stephen Lamoureux at the University of Washington measured it. Casimir was right. To understand why the Casimir effect exists, you need one of the most disorienting facts in modern physics. The vacuum of space is not empty. Quantum field theory, the framework underlying our most precise description of matter and energy, predicts that even perfect vacuum seethes with what are called zero-point fluctuations, virtual particles constantly blinking into existence and annihilating in pairs too briefly to directly observe. These fluctuations fill all of space with a baseline energy that cannot be removed, even in principle. When two metal plates are placed nanometers apart, the confined space between them restricts which fluctuation wavelengths can exist there. Outside the plates, all wavelengths are present. Inside, only certain modes fit. The pressure from fluctuations outside exceeds the pressure from fluctuations inside, and the plates are pushed together. The force between two 1 square centimeter plates separated by 10 nanometers is approximately 10 millinewtons, small but absolutely unambiguous and reproducible. Empty space is pushing objects together. Here's where the mystery deepens into something genuinely disturbing. When physicists calculate how much vacuum energy should exist based on quantum field theory, the answer comes out approximately 10 to the power of 120 times larger than what we actually observe in the universe. That is not a rounding error. That is the single worst quantitative prediction in the history of science. A number correct in its mechanisms, but off in its magnitude by more orders of magnitude than there are atoms in the observable universe. The Casimir effect proves the vacuum has energy. Quantum field theory predicts how much energy it should have. And those two facts disagree by a factor so catastrophically large that the disagreement has been sitting at the center of theoretical physics for decades, with no resolution in sight. Empty space is stranger than anything in it. Number 4. Magnetars, the objects that rewrite physics in a sphere around themselves. At 6:36 in the morning Universal Time on December 27, 2004, a pulse of gamma radiation struck Earth's atmosphere from 50,000 light-years away. Multiple spacecraft, including the Integral Observatory, NASA's Swift satellite, and the Rossi X-ray Timing Explorer, were simultaneously saturated, their detectors overwhelmed. The burst was measurable by amateur radio operators on the ground. It noticeably ionized Earth's upper atmosphere, briefly converting the night-side ionosphere toward daytime conditions. The source was a magnetar called SGR 1806-20, an object approximately 20 kilometers across, roughly the size of a mid-sized city. A magnetar is a neutron star with a magnetic field of extraordinary intensity. SGR 1806-20 carries a field exceeding 10 to the power of 15 Gauss, or roughly 100 billion times the strength of the most powerful human-made magnets. For context, the Earth's magnetic field measures approximately half a Gauss. At the strength of a magnetar, the quantum electrodynamics vacuum itself becomes physically altered. Light traveling through the magnetosphere experiences what is called birefringence. It travels at different speeds depending on its polarization, an effect with no analog in classical physics and no precedent in any laboratory on Earth. The energy released by SGR 1806-20 on December 27, 2004, in roughly 1/5 of a second, exceeded the total energy output of our Sun over 250,000 years. That is not a misprint. A city-sized object, in a fraction of a second, outshone every star in the Milky Way galaxy combined, from 50,000 light-years away, and still managed to measurably disturb the chemistry of our sky. The flare released approximately 100 times more energy than the only 2 previous giant magnetar flares ever recorded. At such field intensities, the familiar rules of chemistry cease to function entirely. The electron clouds of hydrogen atoms, which normally take on a roughly spherical distribution, are deformed into elongated needle shapes by the magnetic force. Molecular bonds as we know them cannot form. The periodic table, as a guide to chemical behavior, becomes meaningless within a magnetar's magnetosphere. This is not exotic speculation. It follows directly from quantum electrodynamics, the most precisely tested theory in physics, applied to conditions no earthly laboratory can replicate. In a fraction of a second from across the galaxy, a city-sized object released more energy than the Sun will produce in 250,000 years, and slightly changed the chemistry of Earth's sky. It was not even the largest magnetar flare theorists believe possible. Somewhere in the Milky Way, objects like this are waiting, and the physics in their vicinity is not the physics of our world. Number 3, the violation of Bell's theorem, the experiment that proved reality is not real. In 1964, Northern Irish physicist John Stuart Bell published a paper in the journal Physics titled On the Einstein-Podolsky-Rosen Paradox. It was at the time considered a niche contribution to the philosophy of quantum mechanics, too abstract for most physicists to bother engaging with seriously. What it contained was a mathematical test capable of determining whether the universe possesses definite properties when no one is looking at it. 58 years later, on October 4, 2022, the Royal Swedish Academy of Sciences awarded the Nobel Prize in Physics to 3 men who spent their careers performing that test. The answer was no. Einstein had been troubled by quantum mechanics for decades. The theory predicted that particles could be entangled, meaning measurements performed on one would instantly constrain the outcomes of measurements on its partner, regardless of the distance between them, faster than any signal could physically travel. Einstein called this spooky action at a distance, and refused to believe it was a complete description of reality. He argued there must be hidden variables, properties the particles carry from the start that merely appear random because we cannot see them. Bell devised an inequality that any hidden variable theory must satisfy. Quantum mechanics predicted that inequality would be violated. Physicist John Clauser performed the first test in 1972. Alain Aspect's team in Orsay, France, conducted a definitive series of experiments in the early 1980s, closing a critical loophole that had left earlier results ambiguous. Anton Zeilinger's group at the University of Vienna spent decades pushing the experiments further, culminating in increasingly stringent tests that addressed multiple loopholes simultaneously. In 2015, a team led by Ronald Henson at Delft University performed the first truly loophole-free Bell test, simultaneously closing the locality loophole and the detection loophole. The result, confirmed with extraordinary statistical certainty, was unambiguous. Bell's inequality is violated. Local hidden variables do not exist. What this means is not an interpretation or a philosophical preference. It is an experimental result honored by the highest scientific prize in the world. Entangled particles do not have definite properties before they are measured. The property only becomes real at the moment of interaction. There is no deeper layer of hidden information determining the outcome in advance. Before measurement, the particle genuinely does not have a definite value. Reality in this precise and measurable sense is undefined until observed. We did not theorize that the universe is indeterminate until something interacts with it. We tested it in laboratories with photons, with rigorous statistics, and confirmed it to a certainty that would be considered overwhelming in any other field of science. The question is no longer whether this is true. The question is what kind of universe we are living in, when true turns out to mean that. Number 2, closed time-like curves. The equations that allowed the past to be revisited. On July 25, 1949, the journal Reviews of Modern Physics published a paper by Kurt Gödel, the logician most famous for proving the limits of mathematical systems, and it described something that shook Einstein personally. Gödel had found an exact solution to Einstein's own field equations of general relativity, the same equations that correctly describe black holes, gravitational waves, and the expansion of the universe, and his solution described a rotating universe in which certain paths through spacetime loop back on themselves. In Gödel's universe, time travel to the past was not just possible, it was geometrically unavoidable. Gödel's solution describes what physicists call closed time-like curves, pass through spacetime that return to their own starting point. Since 1949, researchers have identified closed time-like curves in several other well-established general relativistic solutions. The Kerr metric, derived in 1963 by Roy Kerr to describe rotating black holes, contains regions where closed time-like curves appear near the singularity. Physicists Kip Thorne and Mike Morris showed in 1988 that a traversable wormhole consistent with general relativity would also generate closed time-like curves. Frank Tipler demonstrated in 1974 that an infinitely long rotating cylinder of sufficiently dense matter would create them. These are not fringe proposals. They are published, peer-reviewed solutions to mainstream physics equations. Stephen Hawking found this deeply troubling. In 1992, he published a paper in Physical Review D, proposing what he called the chronology protection conjecture, essentially arguing that quantum effects would always intervene to prevent closed time-like curves from actually forming, protecting the universe from the logical chaos of causality violations. It was a reasonable conjecture. It remains completely unproven. The equations do not enforce it. Hawking was relying on an intuition he could not translate into mathematics. In 2020, physicists Germain Tabar and Fabio Costa at the University of Queensland published work in classical and quantum gravity, demonstrating that quantum mechanics can in principle resolve the classical paradoxes of time travel through self-consistency, meaning that events on a closed time-like curve arrange themselves to avoid contradictions automatically. The grandfather paradox, they argued, dissolves when quantum probabilities are properly accounted for. The barrier to time travel, it appears, is not logical impossibility, but practical physics, the absence so far of anything capable of curving space-time severely enough to create a closed loop. Stephen Hawking spent years arguing that the universe must forbid time travel, and he could never prove it. The field equations still contain that door. General relativity has been confirmed to extraordinary precision in every other prediction it has ever made. And this is the one prediction we are still hoping it gets wrong. Number 1. Dark energy, the force that fills everything and explains nothing. In 1998, 2 independent teams of astronomers set out to measure how quickly the expansion of the universe was slowing down. They pointed their telescopes at Type 1a supernovae, exploding stars that function as standard candles, objects of known intrinsic brightness whose apparent dimness reveals their distance. Team 1 was led by Saul Perlmutter at the Supernova Cosmology Project. Team 2 was led by Brian Schmidt and Adam Rees at the High Z Supernova Search Team. They were rivals, checking each other's work, and they both found the same thing. The universe was not slowing down, it was speeding up. Something was pushing it apart with increasing force, and nobody had any idea what it was. All 3 men received the Nobel Prize in Physics in 2011. The thing they discovered is still unexplained. Scientists named it dark energy, a placeholder designation for whatever is driving the accelerating expansion. The most recent precise measurements from the Planck satellite place it at approximately 68% of the total energy content of the universe. Ordinary matter, everything made of atoms, every planet, every star, every galaxy, every person who has ever lived, accounts for roughly 5%. Dark matter, invisible but gravitationally detectable, accounts for approximately 27%. The dominant component of everything that exists is something we have not detected directly, cannot sample, cannot manipulate, and cannot explain. The leading candidate for dark energy's identity is vacuum energy, the energy of empty space itself, the same zero-point energy that underlies the Casimir effect. Einstein introduced a version of this into his field equations in 1917 as the cosmological constant, later called it his greatest blunder, and was then vindicated posthumously when the 1998 discovery showed the universe behaves almost exactly as the cosmological constant predicts. But when physicists calculate what the vacuum energy density should be using quantum field theory, the answer they get is approximately 10 to the power of 120 times larger than what observations require. This is not an error of refinement. It is the largest quantitative discrepancy between theory and observation in the history of science. More recently, the picture has become more disturbing. The Dark Energy Spectroscopic Instrument, an array of 5,000 robotic optical fibers mounted on a telescope at Kitt Peak National Observatory in Arizona, has been conducting the most extensive survey of the cosmos ever attempted. In April 2024, the DESI collaboration released its first-year results, suggesting that dark energy may not be constant. It may be weakening over time. By March 2025, their second data release strengthened that finding to 4.2 sigma statistical confidence, approaching the threshold required for a formal discovery. If confirmed, this would mean that the cosmological constant, the simplest possible model for dark energy and the one that best fits decades of data, is wrong. Dark energy would be a dynamic, evolving phenomenon, and every theory we might use to explain it would need to be built from almost nothing. Dark energy is not a distant problem. It is not a feature of remote galaxies or the far future. It fills every cubic centimeter of space, including the room you are sitting in right now. It is the dominant component of everything that exists. It is actively accelerating the expansion of the universe, driving every galaxy beyond our local cluster toward an ever more distant horizon from which it will one day become permanently unreachable. And after decades of satellites, surveys, supernovae, and Nobel Prizes, we do not know what it is. We do not know why it has the strength it has. And we do not know whether it will remain constant or continue to change. We live inside the largest thing in the universe, and 68% of it is a mystery we cannot even name properly. That is not a gap in our knowledge waiting to be filled. That is the universe telling us with staggering clarity that the physics we have built is a small candle held against an enormity we have barely begun to see. If you want to see more videos like this, click the video on screen now and make sure to subscribe.